So good evening, everyone. Uh, in today's classes, we will be again solving problems related to your week 8 assignment. Okay, so I will wait for a couple of minutes and then we can solve the problems. Yeah, so let's start the classes and just, yeah, okay, so in these classes, we will more or less continue from last week's discussions, and there are not much, you know, formulas to be given to you. Most of the times, maybe you have already seen it. So we will directly solve numerical problems, okay? And along the way, maybe we can also introduce another formulas and so on, okay? So I will be solving first the questions number two from your assignments, okay? Which says that how does the Fermi wave vector kf depends on the density of particles n in a free Fermi gas. Okay, so the questions is asked, okay, how does the kf, which is the Fermi wave vector, depends on n? Okay, that is the questions, and it's also given to you that it is a Fermi gas. Okay, and in such cases, if you want to find out the number of particles, most of the times it is followed using your density of states. Okay, so if it is a 1D or 2D or 3D, if you know the density of states is the number of states available, then you know what is the number of particles. Okay, so that is how the number of particles comes into the picture. So first of all, you have to know what is the density of states. Then once you know the density of states, we can calculate what is the number of particles. Okay, so now let's first introduce the density of states. So in the density of states, in a 3D, what happens in a cubic volume, let's say in a 3 dimension, in a cubic volume, what happens? Your volume is given by cube, the length cube. That means L into L into L, which is equal to L to the power 3. Okay, this is the volume of a cube. Now, okay, the allowed, in the case space, the allowed values for the wave vector, are quantized. are quantized as what? As k is equal to 2 pi n divided by L, or I can write Ni. Okay, where Ni are integers. Okay, you can take 1, 2, 3 and so on. Now, since each state, okay, is represented by 2 pi n divided by L. So now, each state occupies a volume in K space as what? As a cube of it, 2 pi by L to the power cubed. Okay, that means the volume of each state in the K space is given by 2 pi by L to the power cube. That means 2 pi by L cross 2 pi by L cross 2 pi by L. Indirectly, if you are talking, that means you are talking about 2 pi by L cross 2 pi by L, 2 pi by L. Because why? We are talking about 3 dimensions. So 2 pi by L is for 1 dimension. So in 3 dimension, you have 2 pi by L, 2 pi by L, 2 pi by L, which is equal to 2 pi by L whole cube. Okay, so now you know what is the volume of each state, okay, which is equal to 2 pi by L whole cube. Now, let's say at t equal to 0, okay, we'll take this as reference, t is equal to 0, fermions, because we are talking about a Fermi gas, so you have to also talk about the fermions. Fill all available states starting from lowest energy, right, up to a maximum radius kf. Okay, so so that means, what does it mean? It means that you start filling, the number, depending upon the number of states available, you start filling from the lowest energy up to the maximum that you have, okay, that you can have. So now the total number of particles will be what? This is very important. The total number of particles will be what? N is equal to 2. 2 is the degeneracy into what? Volume of sphere divided by the volume of each state. Okay, so let's take a sphere. That means you can fill particles. And so the volume of the sphere, let's say, is given by something, and if you divided the volume of the sphere by the volume of each state, then you will get what? The total number of states available. So you have the whole volume and divided by the single state, or the volume of a single state, or of each state. That means what you get from this ratio is the number of states available. So once you get the number of states available, you multiply it by 2, you will get the number of particles contained, or the number of particles that can be filled. Okay, so that is what I'm saying, that density of states is you are getting from this. Okay, how many number of states available? Then once you know the number of states available, 2 is the degeneracy. That means you can fill 2 particles in each state. So that's why you get the total number of particles. So the idea is that find first how many number of states available, then you multiply it with 2, you will get the number of particles. So from here, what do you have? 2 into volume of a sphere is what? It's in 3D, we get 4 by 3 pi k f cube. Instead of this is the volume 4 by 3 pi r cube. This is the volume of the sphere, right? But instead of r, you are talking about in case of your instead of, in terms of your k space. So instead of the r, you are just multiplying with a kf. Okay, so 4 by 3 pi kf cube. Okay, so that is the volume of a sphere in k space. Now, what is the volume of each state? That we have already mentioned is going to be 2 pi by L whole cube, right? 2 pi by L whole cube. And L cube is what? I can write it here, 2 pi whole cube, which is also equal to V. Okay, just a second. Yeah, so because L cube we can also write in terms of volume V. So now you can write what? You can write 2 cross, okay, will be simply 4 by 3 pi kf cubed 2 pi whole cubed by v. Okay, by v. Now what will happen? You can write 2 into v, you can take it out, up we get v divided by 2 pi whole cubed into 4 by 3 pi kf cubed. Okay, so you see that how does the number of particles now related to your wave vector? This is the relation. Okay, so if you want to find out the relation, find first the density of states, because from the density of states you will always know about the number of particles that can be filled in those states. Now since you are representing in terms of the k space, so automatically you have the Fermi sphere. Okay, you automatically have your Fermi wave vector kf. Okay, up to a maximum radius kf. Now since you know this, you can easily written to be v kf cubed by 3 pi square. Okay, you just cancel out this 8 on here and 4 here. Okay, and this is 2 into 4 8, and 2 to the power cube is also 8, so you can get cancel it out. Okay, now what happens is that this n divided by v equal to kf cubed by 3 pi square. So from here n by v is in fact, n by v is the number of particles per unit volume. We can represent by small n. So we get n equal to kf cubed by 3 pi square. Okay, so what will happen? This is kf cubed equal to 3 pi square n, which implies that kf equal to 3 pi square n to the power 1 divided by 3. So what do you see here? You see that the wave vector is proportional to n to the power 1 divided by 3. So that explains what is your question. How does kf depends on your number of particles or your density of particles, n is the number of particles per unit, or you can also call density. Density of particles means the number of particles per unit volume. So you see that from here you see that the number of particles, your wave vector, okay, your Fermi wave vector kf, Fermi wave vector is actually proportional to n to the power 1 divided by 3. Okay, now the second question is in this first problem, what did we solve? We solved directly just from the density of states. Simple as that. Use the density of states, you will be able to calculate, or the number of states available, you will be able to calculate. But how does the kf is related to number of particles? That is pretty straightforward. Now, question number B, which says that how does Fermi energy depends on n, again density of particles. So here also what do you have? If you have to calculate Fermi energy, so simply you use this formula. EF is equal to what? H square kf square by 2m. So how do you know this formula? You know that E is equal in fact p square by 2m, right? This is your energy, this is the energy, and momentum is what? Is example h square k square by 2m. So your momentum in terms of k is in fact h square k square by 2m. So this is a formula of your energy. Okay, simply momentum square by mass is equal to h square k square by 2m. So so it is Fermi energy, so you can replace it by a Fermi wave vector. So now what happens? We get h square by 2m, and kf square is what? Kf you know, and you just square. You can just substitute the result from question number A to question number B. So you will get what? Kf square is 3 pi square n. You get 1 by 3 and then square it again. So what you will get? H cross square by 2m 3 pi square n power 2 divided by 3. Can you see? So it's pretty straightforward. Okay, it's pretty straightforward. That means you first find kf, the Fermi wave velocity. How does it depends on n? Okay, once you get that, how does the Fermi energy is easy. You just use the direct formula. EF is equal to h cross square k square by 2m. Then you put what is the value of Fermi wave vector from your the result that you have got from your question number A. So that means here you will get something like EF is proportional to what? To n to the power 2 divided by 3. N to the power 2 divided by 3. Okay, so from the density of states, you know what is the number of particles, and from the number of particles you can also calculate what is the Fermi wave vector, and from the Fermi wave vector you can easily calculate what is the energy. Okay, and now the next question number C of the same questions is, how does pressure depends on n. Okay, this is the third questions. So solution: for a 3D gas, for a 3D Fermi gas, what happens for a 3D Fermi gas? Okay, so you can easily calculate what is the average energy is equal to 3 by 5 n EF. Okay, I will not do it, but you can easily calculate what is the Fermi energy. I mean, what is the average energy in terms of the Fermi energy. So you can calculate what is the total energy of the systems. Again, you have to use the density of state. That is a different the problem. You can follow this F RIF textbooks. F RIF. Okay, Introduction to Statistical Mechanics. It explains clearly how do we get your average energy. So simply, first of all, you have to calculate the total energy by knowing the density of states. Okay, in terms of your energy. So once you get that, you can easily calculate what is your average energy. So this is the so this is your total for the total energy. So sorry, this is not average energy, this is total energy. I will try to say average energy will be E0 by m. Okay, so this is the total the energy. So when I think about total energy, means that it's the sum of the energies of all occupied states. So you have all the states available, okay, in K space, and you fill the particles, and all those particles have a certain energy, and the total energy means the total energy of all the states. Okay, so that the total energy will be in fact 3 by 5 n EF. Again, so once you get EF, again you can do this one. E naught is equal to 3 by 5 n. What is EF? EF, again, you have already known, is this one. So you use the solutions from equation number 2. From question number 2, you get h squared by 2m, and you get 3 pi square to the power 2 divided by 3, and finally we get n by v also to the power 2 divided by 3. So you substitute EF now from questions B. Okay, so fine. So how do we relate? Why I'm doing the total energy? In fact, we have to calculate the pressure, right? We have to calculate the pressure, but why I'm doing this energy? Why is because you can calculate pressure is equal to minus of del E by del V. Okay, so how do we get this formula? Go back to last class. We have shown that your pressure is related to your internal energy as del E by del V. If I'm not wrong, we get du is equal to T ds minus of P dV. From here we get pressure is equal to del U minus of del U by del V. Okay, so it's a continuation of last class. So if you have to find out the pressure, so first of all you can easily calculate what is the energy. So you can calculate del U by del V. So now you can easily differentiate this term, because E naught is already given to you, or in fact U is also equal to E naught, or is equal to, I can just write this simply E here. U is equal to E is equal to 3 by 5 n, and this is EF. So how do you differentiate it? You can just write it out as minus of del by del V. Okay, and energy you can substitute with 3 by 5 n h cross square by 2m and 3 pi square n to the power of 2 by 3, and we get n by v to the power of 2 by 3. Okay, so you just need to differentiate this term, and differentiate this terms which is constant, you can take it out. So we get minus of 3 divided by 5 And also I think h cross square 2m also you can take it outside because it's not required. And 3 pi square also is a constant, you can take it out. Remaining what? Remaining n, this is 2 by 3, and sorry, no, this is, there should not be any n here because I have already multiplied here n divided by v. Okay, so there should not be n there. So n, this is 1 and this is 2 by 3, so n you get f by 3. How do you get that? Because n here is power 1 and you have to add with 2 by 3, so you get 5 by 3. And now the only term that you have to differentiate is del by del v of 1 by v to the power of 2 by 3, right? So, or in other words, I will just rewrite here as simply del by del v of v to the power minus of 2 by 3. Okay, so you can just 3 by 5, this remain the same, h cross square by 2m remain the same, and 3 pi square to the power of 2 by 3 n to the power 5 by 3, this will also remain the same. And what you get, if you differentiate, minus 2 by 3 v to the power minus of 5 by 3, right? This is the standard differentiation. Now what is happening here is that this negative sign, and this negative sign will be gone. Okay, so will be gone. So what you will get, 3 and 3 also will get cancelled, so you will have only 2 divided by 5. Okay, and it's very also interesting here that you can replace again this equation with simply n by v ef, right? Why I'm saying that is because this is h cross square by 2m is the same thing, 3 pi square n to the power 2 divided by 3. Here you can split to what? You can split to n to the power 2 by 3 and n. And here also you can split v is equal to 2 by 3 into v. Correct. So that means what happens? This and this remain the same as your EF, and your unit is n by v. So n by v, which in fact n by v EF. Right? So that means 2 by 5 n EF, since n is equal to n by v. So that means how does your pressure? Your pressure is proportional to n. Okay. So that means 1 n here, that means n to the power, simply n to the power 5 divided by 3. Right, so this is n divided by 3 and this is also volume divided by 3, so you will get your pressure is in fact n to the power 5 by 3. Okay, so that means you can look from here your pressure. If somebody asks how is your what is the equation or what is the formula of your pressure, you can write in this form. Or if how does the pressure related to your number density, or not number density, or your density of particles, then you can write this is n to the power 5 over 3. This is the number of particles, but volume also to the power 2 to the power 5 over 3. So n by v to the power 5 by 3, you will get, and what is the pressure. Okay, so this solves your questions. Now the number 2, which is, what does it mean? It means simply, right, if somebody asks, or if the question is asked, find the number of find the energy or find the pressure, first of all you think whether the density of states is given to you. If it is given to you, then okay, it's fine. If not, you can write the density of states. You can either calculate the Fermi wave vector. From the Fermi wave vector, you can easily calculate what is the energy, what EF, right? From the energy EF, you can calculate what is the pressure also. So that is why this formula, I mean this question is divided into 3 sections, such that we can use the next question from the result of the previous questions. Okay, fine. Now we will move to the next problem, which is question number 3. Okay, so this question number 3 also is is related to a black body radiation. So a black body radiation, I know you must have heard it. All right, it's a black body radiation. So so the question is, find the energy density. Find the energy density rho, which is T comma lambda, okay, which is a function of temperature and wavelength per unit volume, in the wavelength range in the wavelength range lambda and lambda plus d lambda of a black body radiation. You will see that it is one of the standard formula which you have already used before. Okay, so here we just need to find out what is the energy density. That's simple. Okay, of a black body radiation. So we can start this problem, okay, by again I can start this problem by finding the number of particles. Okay, that is also what I will be doing, finding the number of particles. Like in the previous problems we find the number of particles, correct? In the first problems, section A, we find the number of particles. So here also we will find out what is the number of particles. First, before calculating the total energy, first we will find out the number of particles. So the total the total the total energy U in a volume V is the sum of the energies of all possible modes. Okay, so again it's the same sorry, yeah. So if you want to find out what is the total energy, again you have to find out what are the total number of particles indirectly, or you have to find out again is a number of possible states. Okay, and number of possible. So once you know that, you can know what is the total energy. So each mode here, each mode corresponds to what? With wave vector k. With wave vector k has energy, E is equal to h cross omega, right? Is also equal to h cross c k. Why I'm using this energy here? That is because you are dealing with photons. Okay, in a black body radiation you are dealing with photons. Okay, so that is why I named this energy E is equal to h cross omega, which is also equal to h c k. Now, so photons follow what? Bose-Einstein distribution. So according to Bose-Einstein distribution. Why? Because photons follows Bose-Einstein distribution. So if you find out the number of the average particles, you have to use the Bose-Einstein distribution. So it is derived. There is a derivation for to find out the number of particles in a particular state. So that is, you can just have a look at it. So but I will just write the formula. N is equal to 1 divided by e to the power beta h cross c k minus 1. Or if you look at the derivation, it is given to be n is equal to 1 divided by e to the power of beta e minus 1. Okay, so that is the number of particles okay, in a particular state, the number of average particles, or the number of particles, let's say having an energy E, is given by this formula, 1 divided by e to the power of beta e minus of 1. But since in our case your E is actually h cross and the ck, so you can substitute it and the back there, where beta is 1 divided by kt. That in the last class we have already seen that beta is in fact a representation of the inverse of temperature 1 by kt. Now, so now you know the average number of particles. So now what happens is that you can calculate now the number of states, right, between k and k plus dk. So first of all, let's find the number of states between k and k plus dk, which is in fact what you can represent as gk dk. So 2 will comes from your polarization of photons and then again v by 2 pi cubed. You have already seen this one, okay, which is the what the volume of each state v divided by 2 pi q. That in the last in the last problem we have already used this formula v by 2 pi q into what, since it is in an interval dk, you can multiply with 4 pi k square dk. Okay, so this is between between k and k plus dk of a sphere. So if I want to derive this one indirectly, you can write 4 by 3 pi k plus dk whole cube minus of 4 by 3 pi k cube. Okay, if you want to get this 4 pi k square dk, so you will get something like 4 by 3 pi, you extend this formula, and minus of 4 by 3 pi k cube. What will happen is that you can you can neglect whatever, like k square k cube, you can neglect, you can simply get 4 pi 4 pi k square, sorry, you'll get 4 pi k square dk. So how here you k square sorry yeah, k square dk, you leave it. That means you will get 4 pi k square dk, but the term which you have to just assume it to be 0 is 3k d square, right? Since dk is small, so dk square is very small, so you can approximately equal to 0. Okay, that's why you have 4 pi k square dk. So this is the density of states in your interval k and k plus of dk. Now from here you can easily calculate now the energy density. Energy density per unit wave vector. Let's say per unit wave vector, what happens, you get u of k. What will happen? Energy density, so you have to divide it by volume first of all, because it's energy density, and you can multiply n, which is the average number of particles, into the energy into gk. These in fact give you the total energy. So E is the energy and n is the number of average particles. So if you multiply with how much number of density of state that is available, you will get the total energy. Correct. So you know the number of states, you multiply with the average number of particles, you will get the total number of particles in all the states. Now you multiply it with your energy, then you get the total energy of all the particles. Okay, so that means you have 1 divided by v. So n you already know from your from whatever you have, 1 divided by e to the power beta h cross ck by 1 e to the power of beta h cross c k minus 1. Energy is h cross ck, that is already given, and gk. What is gk? Is if you solve these problems here, let me just solve it to make it easier, is simply v by pi square k square, okay, gk. So now is gk is simply v by pi k square, so v by pi k square. So again, if you solve this one, you will get h cross c k cubed pi square will remain e to the power of beta h cross c k minus 1. Okay, this is u of, this is the energy density, okay, per unit wave vector. We are not talking here about k and k plus dk, is per unit wave vector. Now if you have to find out per unit k plus dk, then you just multiply with your dk. Okay, you have to multiply it with with dE, what I'm trying to say. So so now the question is find out in terms of your wavelength lambda. This is in terms of k, this is your energy density in terms of k. But if you have to find out in terms of lambda, what will have to do? You can just replace, using the transformation, right? K is equal to 2 pi by lambda. You know this relation, k is equal to 2 pi by lambda. Then your dk by d lambda will be equal to what? 2 pi by lambda square, right? So now so if you want rho, which is a function of temperature and which is a function of lambda, instead of a function of k, you can write what? We can write du by dk into dk by d lambda. So now the energy density now is a function of lambda. Yes, you can express in terms of dk, but you could use the transformation into dk by d lambda. So now du by dk is in fact this one, right? So we get h cross, yeah, it's h cross uh, h cross c by pi square, and then what will happen, you get also this term h cross c k cubed. So h cross c k cubed, you know k is this much, so you can write 2 pi by lambda whole cube, 2 pi by lambda whole cube. Okay, and then we get e to the power of beta h cross c, and k again you put it 2 pi by lambda and minus 1, and dk by d lambda is also given to you. Dk by d lambda is 2 pi by lambda square. Okay, so now once you solve this, you can just write, you solve, so you get 8 pi h c lambda to the power 5 e to the power of h c by lambda kt minus 1. Okay, so this is your energy density. Your energy density is in fact 8 pi hc by lambda to the power 5 e to the power of hc by lambda kt minus 1. This is your very famous, like very famous formula or laws. You call it as a Planck's law. Okay, for a black body radiation, you must have already seen this formula. So in this case, how do we solve this energy density in terms of lambda and lambda plus d lambda? You use first find out the number of particles using Bose-Einstein distribution. Okay, then you find out the density of states, then you know the total energy between k and k plus of dk, right? Between k and k plus of dk, you know the number of particles. Because you already know the number of particles, you already know the density of state, you can easily calculate the total energy. Now using that one, you can just convert that k in terms of k plus dk in terms of the wavelength. So by using the relation k is equal to 2 pi by lambda. So once you get that, you get what is your energy density in terms of your lambda, which is the famous Planck's law. Okay, so I will not go into the detail of the Planck's law. It is discussed widely in the introduction to quantum mechanics also. This formula is there, introduction to quantum mechanics. I think you must have seen black body radiation. Okay, where you have to modify your classical laws, because it cannot explain the full spectrum. If you have to draw this curve, it will be something like this. This is your, let's say this is your the wavelength, and the lambda, this is your e lambda, d lambda, and so on. Okay, you must have seen this one in many of the textbooks. Okay, fine. So according to these problems, you just need to find out what is the energy density of your black body radiation. So this is done for your for the question number 2. Okay, so yeah, okay, so now let me solve first the problems number 5, because they are more related. Then I can solve the question 5 and 3, okay, later on. Okay, so for the question number 5, what is the question? The question is describe or discuss the expression for the pressure exerted by the non-relativistic Fermi gas at t equal to 0. Okay, also find bulk modulus. Okay, this is also the same problem like the previous two. If you have last question also we solved the pressure, or the first question we solved the pressure. So how do you solve the pressure? First you need to know the energy, because from del u by del v you will get the pressure. Okay, del u by del v. Remember that pressure is minus of del u by del v at a constant, let's say, entropy. Okay, so this is the this formula we have already seen in the last class. Okay, so now what I'm trying to do is again discuss that what is the energy. Okay, and then once we get energy, then we can easily calculate the pressure again. So now you know that energy, I'll give you the formula, is 0 to up to the EF, which is the Fermi energy, and E into GE dE. So if you want to find out the total energy, you have to know what is the density of states, multiply with E from 0 to EF. That means you integrate all the total possible states up to EF. Then you get what is your total energy. Right? This is your formula. And you also know that GE is proportional to E to the power of half. Okay. If you want to do this, you can like separately derive what is the density of states for your one dimension, two dimension, three dimension. You will see this, that your GE is proportional to E to the power of the half. Okay, for the three dimension. Now, so now I will just use whatever the previous result, which says that your average energy is 3 by 5 N EF. So how do I get this energy? If you go back to the first problems, sorry, what is that? 3 by 5 NEF. Okay. Yeah, I'll just use directly this formula. Your energy is 3 by 5 NEF. Okay, so that is, how do we get that? I'll also use the same formula from there, 3 by 5. If it is N here, remember it is a total energy. So this is wrong. This should be simply U. That is the total energy, which is in fact 3 by 5 NEF. So if you do the integration, you will get this formula. Okay, 3 by 5 NEF. So in the first case, I have used 3 by 5 NEF. So how does you get it? You get by integrating EGEDE, integration from 0 to EF. You will get what is the total energy. Now, if I have to find out what is the average energy, U will be equal to U by N, which is equal to 3 by 5 EF. Right? So your total energy is multiplied by N particles. If you have to find average, then you have to find U by N. So now, again, your EF also I will take back from your first problems. EF is equal to what? H cross square by 2m. So instead of kf square, you will get kf square, but I will write kh cross square by 2m. So 3 pi square n to the power of 2 by 3. Okay, I have used again the same formula, this h cross square kh square by 2m. Now, also I can write h cross square by 2m 3 pi square. You can write n by v to the power of 2 by 3, because n is equal to n by v, the number of particles per unit volume. Now, okay, so you know EF. EF is already given to you, and you also know what is the total energy. So you can just replace it what? Therefore, your total energy. This is just exact the same thing like your first problems. Okay, U is equal to 3 by 5, because 3 by 5 N into EF. So 3 by 5 will be there, N also will be there. EF you just substitute here, h cross square by 2m and 3 pi square n by v to the power 2 by 3. Okay, or you can write also as 3 h cross square by 2m. You can write a 3 h cross square by 2m, and sorry, 3 by 10, sorry, not 2m, 3 by, you can write 3 h cross square by 10 m, and you can write 3 pi square to the power 2 by 3. What I'm trying to say is that I can just try to multiply this. So n to the power 2 by 3 into n, we can n to the power 5 by 3. And also this is volume, so you get volume to the power minus 2 by 3. Okay. Sorry. So once you get the energy, pressure is easy, right? Pressure is, you already know, pressure is equal to minus of del U by del V. Okay, so again you can write minus, you can take it out, minus of del by del V, you can put it there, and then what you have to integrate, you have to integrate this energy here that you get 3 h cross square by 10m 3 pi square to the power 2 by 3 n to the power 5 by 3 and volume to the power minus 2 by 3. Why I separate capital N, why I separate small n is equal to n divided by v? Because you have to differentiate with respect to the volume. That is why I separated into n's and v. Now if you do this, if you arrange it and take the differentiation, you will get what? You will get this minus, and this minus which comes from your differentiate will go away. So you will get simply okay, so let me just take it. Let me just take the differentiation 3h cross square by 10m. Then anyway, this will go out because it's a constant term. We get 3 pi square to the power of 2 by 3 and n to the power of 5 by 3 because they are all constants and you have to differentiate with respect to this term. So how do you differentiate? We'll get something like minus of 2 by 3 volume to the power minus of 5 by 3. Okay, so what is happening? Again, 2 and 5, 2 and 10 also will get cancelled, so we get then 2 and 3 and u by v. Okay, you express back these terms in terms of your energy u. Okay, you will get 2 by 3 u by v. Okay, so there is another term. If in case if you want to express in terms of your Fermi energy, you can write simply 2 by 3 and u is what? 3 by 5 capital N E F, correct? And this is v. So you can write 2 by 3, sorry, not 2 by 3, you can simply get 2 by 5 because 3 and 3 will get cancelled. You will get N into E F. If you want to express pressure in terms of your Fermi energy, you can also calculate in this way. Or remember that the formula to calculate the pressure is del U by del V. That is the most critical point. So if you know what is the formula that you need to use, you can easily calculate the energy U. How do you get the energy U? By knowing the density of states. So remember that density of states is the first point that you need to know. If you know the density of states, if you multiply with energy E, you will get what is the total energy of all the states, and you do the integration. Obviously you have to do the integration, at least you have to add up all the possible states and all you have to add up the energy of all the possible states. So once you know the density of states, you know and directly also you know the number of particles, and once you do it, you multiply with the energy, you get the total energy of all the states. So once you get the total energy, it's simple, del U by del V, you will get and what is your pressure inside the systems. Okay, fine. So the first part again is done. This is like a repetition of your first problem. Now the second question, which is already there, is also find the bulk modulus. Bulk modulus. Why this is find the bulk modulus? Because bulk modulus is related to your volume under pressure, right? So that is why it is in these questions you can easily calculate what is the bulk modulus, which is given to be minus of V del P by del V. So you just need to differentiate this pressure V with terms of volume, you get what is the bulk modulus. So what I will do here, first I will just calculate this del P by del V. You can write del P by del V is in fact del by del V. Pressure is what? Pressure is this one, right? Pressure is already given to you in terms of V. So we get 2 by 3 U V inverse, right? So now you can just subtract, you just differentiate. You will get 2 by 3. You can take it outside since it is a constant. So you can write del U by del V, and this remain constant, plus U del by del V of V inverse. This is the product rule. Okay, so 2 by 3 del U by del V is what? Del U by del V. Del U by del V is simply pressure, right? Minus P in fact, because P is equal to minus of del U by del V. So you replace del U by del V to be pressure. So V inverse plus this is negative, so I think you will get negative sign here. If you analyze it, you get U V to the power minus 2. Then you will get what? Pressure to be equal to sorry. So let me just write it here. Your pressure is equal to 2 by 3 U by V. So U is equal to 3 by 2 P V. So now what happens is that your del p by del v is in fact 2 by 3, right? So minus of p by v minus of you can write 3 by 2 pv by v square. V square. So how do I get this problem? Okay, how do I get? I use this relation p is equal to 2 by 3 u and v. I think we have already get here. P is equal to 2 by 3 u by v. So you substitute back here and you get this one. The idea here is to express everything in terms of the pressure and volume. That's it. Okay, you can replace your internal energy in terms of P and U. That is the idea. You can just try to rearrange everything in terms of pressure and volume. That is the idea. Nothing complicated. Okay. So what happens is that now you will get something like if you this v and v square again will get cancelled. You get p by v. So you get something minus 5 by 3 p by v. So your bulk modulus, now you know that del p by del v. So bulk modulus is equal to minus of v del p by del v. Right. So del p by del v is equal to what? Minus v is minus of 5 by 3 p by v. So negative and negative will get cancelled. You will get something like 5 by 3 p by v. Oh, sorry, not p by v. You will get simply p because your v and v will get cancelled. So 5 by 3p. So once you get 5 by 3p, bulk modulus is 5 by 3p, or you can represent this 5 by 3 pressure as again 2 by 3 u by v. That you already know from your first set A of these questions. So you can get 10 divided by 9 u by v. This is your bulk modulus. So these are all are arrangement. Okay, these are all rearrangement to get the final results in terms of u and v. Otherwise, the basic formula is yours. This one is v del p by del v. So you just need to differentiate whatever the pressure that you get with respect to the volume. So that is in fact what gives you your bulk modulus. Okay, so from this problem, what did we get? We have to first we find out what is the pressure. Okay, what is the pressure inside the systems? So the pressure inside the systems you calculate first by knowing the internal energy. So how do we know the internal energy or the energy of the systems? First you calculate what is the density of states and you know the number of particles. Finally you will get the total energy by sum up all the energy states, or if you know the average energy you can just multiply by n. That will also give you the total energy. Then you just differentiate pressure is equal to minus of del u by del v. Done. And if you have to find out the bulk modulus, you have to just follow the equation v del p by del v. Okay, so that is that's it. Okay, so in these 2 to 3 problems, okay, there are there are no like no new concepts. Mainly is the formula which you have been learning, okay, which you all have already seen. How does pressure, volume, okay, and the energy. That's it. Maybe the new concept here is only the density of states, which you might want to read a little more. Otherwise, once you know the density of states, everything will be just use the formula base. Okay, so now we will solve the question number 4. Question number 4 is again related to the Fermi energy. Again, we are going back round and round all the same problems. Okay, so the idea is find the density of states for the Fermi gas, or for in 3D, let's say for the Fermi gas for a 3D, find the density of states, find the energy, find the Fermi energy. Then once you got the Fermi energy, you know what is the Fermi wave vector. Once you know the Fermi wave vector, you also know what is the Fermi temperature. So all of these are not simple, they are all not related. Okay, now so yes, so here the questions number 4. The question number 4 is find the Fermi temperature. Find the Fermi temperature of sodium whose density is 0.95 gram per cc and atomic weight is 23. Okay, sodium has 1 conduction electron per atom. Okay, so here again, if you have to find the Fermi temperature, EF is equal to KBTF. Use this formula. So this is just a thermal energy. Okay, that is a thermal energy. KBT is a thermal energy. So you know EF, you know TF, which is the temperature. So again, now you have to find out what is EF. EF you already know for for the formula of EF is simply what EF is equal to what? It's equal to simply h cross square KF square by 2m, and we have already seen how does KF square relates, simply 3 pi square n to the power of 2 by 3. Right, this we have already done in the previous problems. That means your Fermi wave vector is proportional to 3 pi square n to the power of 2 by 3. Now what you need to find, h you know, m you know, you just need to find n. How do you find n in such problems? Given the density, given the atomic weight, right? Given the atomic weight, how do you find the density, the number of particles? So use this formula, n is equal to rho Na by m. Okay, that is the number of particles. You can, it's related to the density, the Avogadro's numbers divided by the molecular weight. So what happens to density? Density is 0.95. Okay, and A is 6.023 into 10 to the power 23 in terms of mole, and mass is given to you, molecular weight is given to you 23. So 23. Okay, if you want to write in terms of kg, that is also fine. You have to express this 0.95, the density, in terms of kg, and also your you have to express everything, all these terms in terms of your the kg, if you want 0.95 in terms of kg. But here I have used the CGS unit because this molecular weight also I have to use gram per mole. So that means they can easily cancel one another. Otherwise, your density 0.95 gram per centimeter cube, you have to express in terms of gram per meter cube. Okay, if you want to use in terms of SI, the SI unit, then you will get in terms of the number density in terms of your meter cube. So what I will do here, this is in terms of CGS unit. Remember, this is CGS unit, so you can get, if you substitute this one, or if you take the multiplication and divide, you get 2.48 into 10 to the power 22 centimeter cube. Okay, remember, because I use the density in terms of CGS unit. If you want directly to convert this in terms of your the SI unit, then you can easily get it directly in terms of meter cube. Okay, so if I want to express this one into meter cube, it's easy. 2.48 into 10 to the power 28 meter cube, because you can use the formula 1 centimeter is equal to 10 to 1 minus 2 meter. Okay, so once you know the value of n, then you automatically know, because you use this formula EF, Fermi energy. Then once you get EF, you can use this formula TF. You know, you get the final result. Okay, so EF equal to h cross square 2m 3 pi square n to the power 2 by 3. And if I have to write it here, h cross square is simply 1.05. H cross you can write h by 2 pi, right? Okay, so h is equal to 6.034 10 to the power minus 34, and you can substitute here h cross. So 1.05 into 10 to the power minus 34 divided by 2. M is the mass of your electron, which is simply 9.1 into 10 to the power minus of 31 kg. So I solved everything in terms of SI unit now, and get 3 pi square. N is what? N you have you got to be 2.48 into 10 to the power 28 to the power 2 by 3 to the power 2 by 3. And finally you will get something like, if you solve it, you get 6.05 into 10 to the power minus 39, the first term, and the second term you will get something like 7.364 into 10 to the power, let's say 29 to the power 2 by 3. Okay, you just confirm it. Okay, I have solved this, so I just give you the your final calculation, but you can cross check it. Okay, now what happens is that then you have to again take the power of this term, of the second term, so we can get 6.05 into 10 to the power minus of 39. Sorry, so you can go directly, you can write directly now 6.9 into 8.13, because this comes from the second terms, into 10 to the power minus of 20. So what is the unit of this? This should be joules, because this is in terms of SI unit. So we get 4.9 into 10 to the power minus of 19 joule. This is your EF. Okay, that is your Fermi energy. Now once you get the Fermi energy, then what else? You can get EF is equal to KB TF. So your TF is simply EF by KB. EF is 4.9 into 10 to the power minus of 19 joules, and KB is 1.38 into 10 to the power minus 23, which is approximately 3.6 into 10 to the power 4 Kelvin. Okay, maybe just write it here. 3.6 into 10 to the power 4. Okay. That means close to 10 to the power 5 Kelvin, or 3.4 into 10 to the power 4 Kelvin. You can just cross check the calculation, okay? But this is how the way you solve. So if I want to find out what is the Fermi temperature, so the best thing is to calculate first the energy. And how do we get the energy, EF? You can easily calculate the value of energy EF by using this formula, h cross square k square by 2m, or h cross square kx square by 2m, and kx square you easily calculate in terms of 2 pi square n, 3 pi square n to the power 2 by 3. If kf, if the Fermi wave factor is given to you, then you use directly. Otherwise, if kf is not known, then kf again is directly related to your n. Okay, so if I want to summarize this, what happens? First, we calculate kf to n. Right? How does this kf and n are related? Now from n, from your kf, you can calculate EF and related to your energy kf. Right? And then from there, once you know EF, this is also related to your temperature TF. Right? So, or I would rather say this is TF is related to your energy EF. So KF, so if KF is not given, first find what is the value of n, right? The number of particles, then you know K of F. Once you know K of F, you know what is the Fermi energy, and once you know the Fermi energy, you know what is the Fermi temperature. So all of these are connected to one another. Okay, so you just need to find out what is given to you and how do you tackle the problems. Okay, this is few sets of formula. Okay, that's it. Now there is one final problems, okay, which I will solve, then I will stop it here. Okay, it's a little different, but the question number 1, then I will stop it. Okay, and then I will stop. So so what is the problem? The problem is how does the Bose-Einstein condensation, Bose-Einstein condensation temperature depends on the density of particles. Okay, so this is the questions. So so let me just write the definition of these Bose-Einstein condensation. So the Bose-Einstein condensation, you call it as BEC, temperature. Okay, they can say TC is the critical temperature, below which boson occupies the lowest quantum state. Okay, so it is the temperature or the critical temperature in which below most of the bosons or that fraction maximum fraction of the bosons will occupy the at the lowest quantum state. Okay, so so again, you know, n we can represent n to be simply n divided by v. Okay, we can use the same notation here. We will use the same notations that for your bosons again, your the density of particles, just like here, the density of particles. We can it means you know total number of particles per unit volume. Okay, now so the condition I'll just write the condition the condition the onset for the onset of condensation occurs when chemical potential mu reaches the ground state energy, or I will write how does is related n equal to 1 by lambda cube zeta function of 3 by 2. Okay, so this is how your de Broglie wavelength lambda here is your de Broglie wavelength. Okay, your de Broglie wavelength, and your de Broglie wavelength lambda is equal to h square by 2 pi m kt. Okay, so the relation is that you know the relation between the number density and your de Broglie wavelength. So and de Broglie wavelength is also related to your temperature. So now the question is that how do you relate your temperature T with your number of particles? So it's pretty straightforward. Now you can just write n equal to, you can just substitute 1 by lambda or 1 by lambda cube with this formula. So you will get 2 pi m kt by h square to the power 2 by 3, correct, and zeta function of 3 by 2. This anyway, this is a constant terms. So so that means now the critical temperature, if you replace this one c, then you also have to this is a critical temperature, so your Tc will be equal to what? Will be equal to h square by 2 pi m kb. That is one thing, into, okay, n to the power of n to the power, where is n? Okay, sorry, n to the power of 2 by 3. Okay, and zeta function of 3 by 2 to the power of 2 by 3. Okay, so your Tc is in fact proportional to n to the power of 2 by 3. Okay, so how does the number of particles related to the de Broglie wavelength? That you need to know. So the number of particles related to the de Broglie wavelength for the for Bose-Einstein condensation is proportional to 1 by lambda cube. Okay, that means the number of density is proportional to 1 by lambda cube. Then lambda, you know, is a de Broglie wavelength, which is again given by the square root of h square by 2 by mkt. Then you substitute in terms of lambda cube, you substitute 2 pi mkt, then you relate what is n and t. So that is Tc is proportional to n to the power of 2 by 3. Okay, now the question B says how does the number of particles in the condensate depends on temperature. Okay, so I will write here, let's say below your critical temperature, in which below this temperature you have a Bose-Einstein condensation. So below Tc, the number of particles in the excited states, I would rather say in the excited states, I remember is an excited states is limited by, or is constrained by the maximum capacity of the excited states at that temperature temperature given by what? N excited of temperature is given to be N T by Tc to the power 3 or by 2. Okay, so that, how do you get T by Tc? You get again from this relation again. N is proportional to 2 by 3. Okay, I think I made a mistake. Sorry, I think I made a mistake here. It should be 3 by 2. This is not 2 by 3. This should be 3 by 2. Okay, it should be 3 by 2. So here also you get 3 by 2. So n is limited by, by the number of states available at that temperature. So n excited state is given to be N T by Tc. So now, number of particles in the ground state, number of particles in, let's say, or occupying the ground state, I will rather say occupying the ground state is what? Is N0 is equal to N minus of N excited state. Or in other words, we get N is equal to N0 plus N excited state. That is the total number of particles is equal to number of ground state plus excited state. So N naught in the ground state, we get N minus of, we substitute here, N excited is equal to N T by Tc to the power 3 divided by 2. So you can take common N, you can write 1 minus of T by Tc to the power 3 by 2. So N naught in the ground state, or N naught divided by N, right? N naught proportional to T to the power 3 divided by 2. Okay, so how does the number of particles in the constant depends on the temperature? It depends to be T to the power 3 divided by 2. Okay, so N naught is the number of particles in the ground state. Okay, that means or in the below Tc for T less than Tc. So if N naught is proportional to Tc to the T to the power 3 divided by 2, then you can just substitute here N naught divided by N is equal to 1 minus of T divided by Tc to the power 3 divided by 2. Okay, so we are almost done. Okay, so the question C that how does specific heat, now how does specific heat depends, or the question is plot the behavior of specific as a function of temperature, depends on temperature for an ideal Bose gas. So what you can write is that I can just plot here Cv, this is your temperature T, and this is your critical temperature. You'll get something like this and then like this. So below T so in this below T to Tc, you will have something like T to the power 3 divided by 2, purely dominated by the excited state particles, and greater than T to Tc, you will have something like 3 by 2 kBT, approximately 3 by 2 kBT. Okay, so that is how you specify it. And finally your last question is, that is question number D, which is state Boltzmann law, Stefan Boltzmann law. So what I will just write is just J is equal to sigma T to the power 4. So Stefan Boltzmann's law, what happens, it says that that the power radiated, this is the same thing as your black body radiation, right? The power radiated in terms of your temperature, it relates how does the energy radiate from a black body radiation with temperature. So J here is in fact what? J here is the amount of energy radiated per unit area, power per unit area. This is power per unit area. That means the amount of energy, or I would rather say the amount of energy emitted per unit second or per unit time is in fact proportional to the fourth power of your temperature. That means the amount of energy emitted by a black body radiation is proportional to the fourth power of your temperature. That is the Stefan Boltzmann law. Or you can write for an area A, let's say this is this, because this is per unit area. For area A, we can write power equal to A sigma T to the power 4, where A is an area and sigma equal to 2 pi to the power 5 K to the power 4 by 15 C square H cube, which is equal to 5.67 into 10 to the power minus of 8 watt per meter square Kelvin. So Stephen's Boltzmann law is simple. Stephen's Boltzmann law says that 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 the amount of energy emitted per unit area per unit time is proportional to the fourth power, to the fourth power of your temperature, and that is per unit area. If you have to find out the total area, we just multiply by A, which is the total area. And area, it could be 4 pi r square, it could be a circle, it could be a cube, and so on. Okay, so finally, for this week, I am done with your 5 questions assignments. So we will meet again next week. Okay, I will upload. If you have any questions, you can always send an email, or I will upload all the news and not the news and the notes in the drive. Okay, so thank you so much. I'll see you next week.